והבאנו בעצם את מרק לבוא להרצות לנו. כמה מילים קצת על דיסים, מישהו פה חדש ככה לאירוע, אז בעצם אני ויפתח עמית, מארגנים את מפגש של DefCon הישראלי, DCS 2-3, מפגשים כל חודש, יש לנו וויקי, אנחנו מנסים לעשות דברים גדולים ומגניבים. אחד הפרויקטים כזה אנחנו מנסים להריץ זה בעצם ההאקתון, אולי שמעתם, אולי קראתם, זה גם מקום טוב לדבר על זה בכמה מילים. ההאקתון הוא בעצם סדנת hands-on, זה הרצאה, בהאקתון בעצם אנשים יושבים, כותבים קוד ביחד, חוקרים ביחד, מפתחים ביחד, אני מפתח כרגע עובדים בעצם לארגן את זה, אנחנו בשלבים מאוד מתקדמים, ובתקווה יהיה אפילו announcement בימים הקרובים. טוב, בלי יותר מדי ככה לדבר, אז בעצם מרק הגיע פה לארץ לחופשה, הוא הסכים להתנדבות לתת פה להרצאה, זה מאוד נדיב מצדו, אז תהיו מאוד ישראלים ואכפתיים. אוקיי, so without further introduction, please have Marc and Hauser use.
Shalom, hello everybody. Thank you for inviting me. I have no clue what he said. Could be anything. I heard something like karate. I don't do karate if he said that. No clue. But it might be true, whatever other thing he said. Yeah, I'm here to talk about a little bit of what I did in the last 1 year on IPv6 security research. Yeah, so let's start. So who am I? Marc, or more people will know me as a Hauser from THC. I'm doing IPv6 stuff since 6-7 years now already. So even before there was really IPv6 there, I already looked at what could be done there. And it's really scary, but you will see that, don't worry. So who of you has already heard my previous talk I did 5-6 years ago? Okay, 1 guy, 2, 3, okay, that's good. Who has played already with IPv6 so far? That's pretty good. I would say it's 30-40% something, pretty good. Who has IPv6 at home or in the company or at the university or something like that? That's all pretty. Okay, forget the home, university or company. Okay, no that's good. 3-4, that's not so much. Yeah, IPv6. Many people thought, okay, this is something which will never ever happen. So it's like Star Wars universe, and we all know the X-fighter will never fly, and yeah, so this will hopefully just go away if we ignore all the problem. Well, today we know IPv6 is already there. It's among us. We have it on all our operating systems. If it's not FreeBSD, it's all activated IPv6 by default. So it's already there. And now that the IPv4 registry says there are no IPv4 address space left to hand out, we will get it pretty soon. For example, in Germany this summer, the pilot starts to get IPv6 on all the DSLs. So until the end of the year, every DSL should be dual stack IPv6, IPv4. So this is something which is within the next 12 months we all will encounter some way or another. Is this actually working here? This one should, I have 2. The first time I have 2. It's like kids, maybe I should put them here. Okay, but here I don't. Hey, Total Recall, nice movie. So, now I have it. Good work. Okay, let's start with IPv6 basics. In IPv4, we have 4 octets. This is a standard IPv4 address. We have 4 billion possible IPv4 addresses. In IPv6, we have 16 octets, which give us such a large amount of IPv6 addresses. I don't know how to say this large number, and this is how an average IPv6 address looks like. So how is such an IPv6 address being built? In the beginning, so every 2 octets are combined and presented in hexadecimal. So there would be 8 representations which are all separated by colons. As you see, there are not 8. I'm coming to that. If there is their leading 0, this can be omitted. So this could also be written as 0004. And if there is the longest chain of 0:0, colon is replaced with 2 colons. Yeah, so this would be all filled with 0, 0, 0, 0. This is how an IPv6 address looks like. Yeah, and even that, I mean, it's a very, very easy address, but still it's more complicated than an IPv4. Every subnet, and this is how it has to be, otherwise many things won't work, are /64. It means every subnet on every network is 4 billion times larger than the whole internet. That's just the average subnet. So we don't have any broadcast addresses, we have multicast addresses, but multicast addresses are only in your local domain, which means the multicast address is always the same. Yeah? It doesn't, your multicast address is the same as in another location, the multicast address, they're all the same everywhere. So if you access your multicast address just in your region, so you can't access any addresses from a remote network. And we have lots of features. We have auto configuration, which is, in my opinion, a very, very cool thing. The idea here is you plug any device anywhere and you have network connectivity out of the box. You don't have to do anything. Like DHCP, but without the need of DHCP, it's all in the IP protocol. You have IPsec mandatory within the protocol. You have mobility option. Mobility means, let's say I'm here on a wireless LAN IPv6 network, and I'll take my laptop, go on a train, go on another wireless LAN IPv6 network, go into some internet cafe, hook up maybe via Ethernet LAN, then I fly over the sea to New York, all keeping my connections open, keeping the same IPv6 address. Yeah? That was mobility means. And of course, enough addresses until the end of the next 5 years, until they're all again depleted. So the thing where people saying, oh, IPv6 will enough address for the next 20, 30, 40 years, I don't believe that actually. So in my opinion, these will also be depleted very fast. Okay, this is how an IPv6 header looks like. And if you look at it, okay, it looks bigger as an IPv4 header, and it is. But it also looks much simpler because stuff which is in the IPv4, bad boy, was omitted because things were removed where they thought this is not important anymore. So, who can spot the differences here? Okay, you? Yeah, where are the options? So there could be maybe options here, like options are optional, yeah, that's the name, but in IPv6 there are no optional options. So these are missing. You know why?
Yeah, because they're being put on the end.
Yep. Okay, what I'm looking for, the answer is the options are not in here.
Because the size of the
exactly. The goal was, that was very important for the router manufacturers, that the header has a fixed size, and it's always that fixed size, because then it's way easier to handle in the router. It's always 40 byte. Someone else was saying something about what else is missing? Yes, when they defined the protocol in 1995, what they did, they renamed all the names of the protocol entries just to make things harder. Really, no other sense at all. So hop limit is time to live, yes.
The lengths don't include the headers.
Exactly, because the header is now fixed, so we don't have to include this in the length. Yes, that's true. Yeah, where's the checksum? Really, there is no checksum anymore. Reason for that, they say now, the networks are now reliable, so we don't need a checksum here. And they say the checksum is now on the upper level protocols, like TCP, but now also ICMP mandatory has to do checksumming. Yeah, not in ICMP4, yeah, there is no checksums. Okay, who else sees something missing?
Don't have fragmentation.
Yes, there's no fragmentation. How can this work?
Jump of time.
You are not fragmenting. You are not fragmenting.
Exactly. Of course it doesn't work. So there will be fragmenting somehow, and I'll show you with the next slides. What else is missing?
There was a thing with IP ID.
Yes, IP ID was removed. The reason for that, in the beginning, IP ID was there, so if there's packet duplication on the packet path, yeah, so the router somehow, for whatever reason, would send it 2 times there and there, you can see, okay, now this is a duplicate packet, we can see it from the IP ID, and so we can ignore one of them. But then that was when IPv4 was designed. But later they noticed, oh, we don't need that. So here it's omitted. We don't need it anymore. OK, so let's have a look. There is no header length anymore because the length field now just shows the payload. We have no IP ID anymore. There is no checksum. There is no fragmentation. And there are no options anymore. So that's why the header looks so simple. And everybody knows if something is simple, it's way easier to implement and less error prone. So it should have less security problems. Everything which is an option is now an extension header. We have fragmentation, we have source routing. Yeah, we have source routing again. We have IPsec, we have destination options, and we also have hop-by-hop options and some other stuff which we can ignore for a moment. So everything is an extension header which is optional. This is how it can look like. Well, maybe I should. You have the IPv header. In the IPv header, we have this, which means what is the next header? What is the next protocol we are carrying? So here there would be 43, which would be the routing header, so source routing. There we have the next header 44, which would mean we have a fragmentation here. And here would be 17. That would mean here's the UDP packet and the data of the UDP. Yes?
Does it mean that we can have multiple routing errors, for example, for source routing next hops is omitted?
Let it put it like that. Even looking at this shows you that can be lots of problems. And when they designed that, even the operating systems vendors implementing that stuff, they don't have a clue what can happen. So yes, you can put 50 routing headers there if you want to. What will happen? Depends. Nobody can answer you that. Because the RFC doesn't define there may only be one routing header. Nothing like that. Yeah? Could there be more than one destination header? Yeah, there could be. Because the standard says it can be. You should not. That's what's in the standard. You should not. But you still can. So could there be trouble? Yes, there will. So in theory, IPv6 first looks way simpler than IPv4. OK, the addresses are longer, but the protocol is way simpler. But yeah, ranting. The problem is that IPv6 was designed with people knowing not so much about security. So everybody who's telling you IPv6 is secure, what they mean is it has IPsec. Yeah, that's what I mean is IPv6 is secure. It has IPsec. Well, every IPv4 implementation you see today also has IPsec. So is IPv4 secure? No, of course not. And they also didn't have much clue about what they're really doing. For example, if you want to do internet stuff and networking stuff, what you need is DNS, right? I mean, how can you work on the internet and do stuff without DNS? It doesn't work. So when they did the auto configuration thing, so you can plug your system anywhere, yeah, and network connectivity works out of the box, what they forgot was to add DNS server. So you can plug your system anywhere, but you don't have any DNS information. Yeah. So in the beginning they said auto configuration will replace DHCP. No DHCP anymore. But what happened then is when they found out, oh, we forgot to add the DNS server, well, we could use DHCP, so we use auto configuration for the IP information, but we use DHCP for the DNS information. Yeah, it makes total sense, right? Which shows their sense of, oh, yeah, and many more things they did wrong. So what happens next is what always happens with when network people try to solve a problem, they find multiple solutions. And it's up to the vendor to decide if they go path A, B, or C. And everybody selects a different path maybe, and then you're fucked. So you can use DHCP for that. You can also use a new RFC option, which does that in the router advertisement, which is the auto configuration. Or there's a third option that is a special multicast address, which is used for DNS servers. And it depends on what the vendor thinks is the right choice, what you get. And there are many more things where IPv6 is just wrong. Yeah, you have to keep in mind that IPv6 was designed in 1995. Fun fact, THC group is 2 months older than the IPv6 protocol. Yeah, but 15 years ago, the security model was everything local is trusted, everything on the internet is not so trusted. Yeah, but something like third parties or partially trusted network or open networks, that was not part of the security concept. That was not in their mind. And that's what you have now in the protocol. The same things you find in IPv4, you have in IPv6, and no real change. So this is the list of IPv6 vulnerabilities you have in the CVE. So as you know, you have way more IPv6 vulnerabilities than just the stuff in the CVE, but it gives you some statistic. So in the beginning there was not much, simply because, well, nobody was using it. So nothing much can happen. Yeah, what you can see, this is the current numbers. In 2000, well, in the CVEs, which are numbers which are shown for 2010, when you get a CVE number, you don't immediately publish. You wait for the vendor to supply a fix, and this can take maybe a year. That's why even now we have May, not all CVE numbers for 2010 are already published. So there's still some open. And for 2011, we have already, but this is a number from beginning of April, so it's already 1 month old. We already had 5. Yeah? So I predict that at the end of, now let's say in summer 2012, when all the numbers with CVE 2011 have been announced, that we'll get to something like over 20 vulnerabilities. Because now it's being used, so more is found. Natural way of life. And we see IPv6 is so not easy to implement and very, very error prone. I will show you that later in some examples. So, and that not even, so this does mostly, so I think there's only one CVE open of mine which is not yet in the 2010, but here are also some which are not yet published. Some even doesn't have a CVE yet. So there's more to come. So kids, in 2005, okay, so you know how I Met Your Mother? Okay, I like the show very much, so. So kids, in 2005, I did my first presentation on IPv6 insecurities, and that was just the basic stuff. So this is how you do man-in-the-middle stuff, etc., etc. So I will just wrap that up in 5 minutes, and then we do all the new cool stuff. So in the beginning, I had to program my own toolkit, because in 2005 or 2004, that's when I started to program that, there was no packet library which had IPv6 support. So I had to program my own packet library. So that's why there is a special toolkit. That was the only reason. Otherwise, I would have used libnet or whatever. But there was nothing, so I had to write my own. It was a pain in the ass. So if I could have used the time maybe better for something else. So first we have ARP spoofing. ARP spoofing has an IPv4, and we have the same in IPv6, but there it's called neighbor discovery spoofing, because there is no ARP anymore in IPv6. This is now done in ICMP version 6. And because the process is called neighbor discovery, that's why it's called neighbor discovery spoofing. It works exactly the same like ARP. You have a neighbor solicitation, so the ARP request you send on the network, and the system who has this IPv6 address that is asked for replies with a neighbor announcement. This is my MAC address for this IPv6 address. But this is all multicast broadcast on the network. Anybody can see the solicitation request and answer and give a fake answer maybe to that. And I wrote for tool to that is Parasite 6, that you can do easy man in the middle on your local IPv6 network. Really, really simple. Then we have duplicate address detection denial of service. Works like that. If a system gets a new IPv6 address, it has to check on the network that nobody else is using that IPv6 address. So it also sends a neighbor solicitation request for that IPv6 address it wants to use, and checks if there's anybody answering that request. What you can do is listen to all these requests and then say, I have this IPv6 address, I have that IPv6 address, and yes, your next request, I also have that IPv6 address. And then the system can't join the network because it doesn't get an IPv6 address. So very easy denial of service attack, and works out of the box for all the OSs. Then we have a man-in-the-middle attack with redirects. Who knows about ICMP redirects on IPv4? Okay.
Number 5.
Yes? how do you do a man-in-the-middle attack with redirects with secure redirects on? Secure redirects works like that. In former times, redirects was just you get a message from your router, which tells you, okay, this target is now over that router. You put that in your routing table, done. Yeah, sucks. Yeah, fix me, I'm broken.
You seem broken.
I seem broken, thank you.
If this doesn't work.
Okay, I'll try, yeah. Sorry, that's too hard for me. Okay, secure redirects means because they finally recognized that this is a problem. If just a router, the default router, seemingly default router, but anybody can create that packet. So this can be easily spoofed. So a secure redirect means only if a system sends a packet outwards and exactly this packet is reported for wrong route, take another route. Then this routing change, this redirect is processed. This is called a secure redirect because the system must have sent the packet which is said no, it should take a different route. As only the default router sees that packet, redirects are secure. How can this be circumvented? Oh, that sounds pretty complicated. Nah, hacking is way simpler than that. Don't think complicated, think simple. Think simple. What you need to do is send a message, spoof from the system you want to redirect the traffic for, and know what the answer from the system will be. So what the easy process is, you spoof a ping packet seemingly coming from the target to the victim, and you know how the answer to a ping looks like because you spoofed the ping. Yeah? So you spoof the ping packet, the echo request. Based on the information, you know how the ping reply would look like. You create the redirect information, send the redirect, done. Yes?
What do you do if the victim is using a firewall and proxy of your packets?
In IPv4, this is your problem. So this could not work because of that, but you can check before. If you can ping the target, everybody can ping the target, and then you can spoof that stuff. On IPv6, this is the only thing in IPv6 where it's more secure than IPv4. And that is this attack now works only locally. I can spoof the ping to come from a very remote target, but to redirect the traffic for me to send the redirect, I must be local on the network. Because I have to set in the redirect packet a time to live of 255. And the victim would only accept the redirect packet if it still has a TTL of 255. So if it's coming over the router, it would decrement the time to live. It's 254, for example, and will ignore the packet. That's why it's not working remotely anymore in IPv6. But this is how you can easily do that. And then we have DHCP, and DHCP is auto-configuration IPv6. It does not necessarily needs a router solicitation. So all it needs is a router sending a router advertisement saying, I'm a router, I'm your router, baby. It has options, and if it has the auto-configuration flag set, every system on the network will configure an IPv6 address based on the network configuration in that packet. Yeah, but cool. Sick, but cool. Yeah, this is how it works. Yeah, in my opinion, it's pretty cool. Yeah, it's really effective. You don't need an extra server for that. Yeah, it's all in the router. Wonderful.
Instead of on ICMP message number 9 and 10, you could advertise yourself as a router. But everybody blocked it, right?
Yeah, the problem is here now. You have to use it. Yeah. In DHCP, if you say, I want to use DHCP and not auto-configuration feature, DHCP has no option for routing information. Yeah? So you have to do router advertisement. There's no way around that. And I will show you later 3-4 attacks on that. Yeah? So, And now DNS is also an option, but not all systems support that. So for example, Linux, you need an extra daemon for that to get that information. Yeah, but what everybody can do is say, yeah, I am a router too, and I'm also your default router. Yeah? But I have a higher priority, because there's a priority flag, and by default it's all on medium. But if you set your priority to high, well, you are the default router. In the tool I wrote, fake router 6 does exactly that. Says I'm the local IPv6 default router, I have the highest priority, send all your packets to me. So yeah, new and improved stuff. So this was the stuff from 5 years ago. You can easily kick the default router. Yeah? Even if this has the default router has the priority to high. So, and he is first and you come later. So this is still the default router. So if we send our own router advertisement, this is still the default router. Too bad. But there are ways around that. We can spoof a router advertisement seemingly coming from that router, but setting a lifetime of 0. This is what this router would send if it's shut down. To tell everybody on the network, I'm going down, I'm not available anymore, my lifetime is 0. In that moment, all the systems on the network remove that routing entry for this router. Just to be sure, I resend my router advertisement afterwards, and I'm the default router. Yeah, it's so simple. No need to do any complex things. Once they got more security, we can start with the complex things. But so far, why use a big machine gun for some small bug? We can even send this spoofed router advertisement in a way on the network that this router will never see it. We'll come back to that later. So we can also use a router advertisement for systems to become dual stack. This happens if we have an IPv4 only network. There's only IPv4 on the network, no IPv6, but still we can attack them on IPv6. Only we have to do is send a router advertisement, and they automatically activate IPv6 and configure their IPv6 IP address. And this can now be very easily scanned. And if you are one of those guys who have a Linux box and say, yeah, I'm writing my own firewall rules because I'm clever and all the operating system vendors are dumb, they don't know how to write firewalling rules, well, it's the other way around. You're dumb, they know better. Because what most of those people forget is that IPv6 is in a different module, a different protocol stack. All your filter rules you wrote don't apply to IPv6. So you need to configure an IPv6 firewall to protect your ports on IPv6. And if you haven't done that, just by sending a router advertisement in your system, configuring itself automatically an IPv6 address, I can attack you on this address and bypassing your IPv4 firewall rules. Yes?
What about the bind address of the socket? If it is bound to an IPv4 address,
then this wouldn't work. The feature of all modern operating systems, if it's Linux or if it's Windows, doesn't matter. They are already IPv6 aware, so most of the services are already running on IPv6. But just because they don't have a public official IPv6 address, you can't access them. If you know the link local address is something I'm not going into now, you can even do that without a router advertisement, tag them on the local network. So what is also nice, once they are dual stack, they will prefer IPv6. Kind of depends on the operating system. For example, this is true on Linux. Windows also now starts to prefer IPv6. It means if you get the information, you can get to a destination you want to go to via IPv6 and IPv4, the system will choose IPv6. Wonderful. So we have an IPv4 only network. I send a router advertisement. System thinks, oh, I have IPv6. Yeah, let's use IPv6. Yeah? And also another way on doing man in the middle and get all the traffic to your system. Yeah, you can also announce important networks being local. This is very easy because on IPv6 you can have many addresses, not just one IPv6 address. You must have to communicate on a network 2 IPv6 addresses at minimum, and you can have unlimited IPv6 addresses. So I can announce more and more and more networks which don't belong on your network on the local LAN, and your system thinks it's all local. Yeah? Google, PayPal, Amazon, it's all local. Yeah? Pretty nice. And then we have one thing which is called router advertisement flooding. I found that 10 months ago or something, just by playing around. I mean, imagine I send a router advertisement on the network saying this is the local network, and all the systems configure their IPv6 address to that. Okay? Now, I sent another router advertisement telling I'm a different router and I'm announcing a different network. What happens? All the systems configure an additional IPv6 address. And now what happens if I pretend to be 1,000 different routers announcing 1,000 more different kind of networks? What could probably go wrong? Well, I expected this is such a simple attack that nothing would happen. So it was a pretty surprise for me when all the Cisco products had big issues with that. The NetScreen firewalls, all the Windows systems with IPv6, FreeBSD and old Lions. They actually recognized the problem 2 years ago or something and fixed that. But everybody else didn't. And it surprised me. And that really shows you what their mind is on IPv6. They're implementing something, but they're not actually evaluating the risks which come with that. Just blindly implementing. Yeah? So what happens on FreeBSD, 100% CPU, you can't use the system really anymore, and sometimes the IPv6 protocol stack breaks. So there's no IPv6 anymore. You still have your interface stuff, but no IPv6. It's gone. Yeah, what happens on the firewalls in Windows is 100 CPU, 100% RAM. That's it. Yeah? End of system life. And only when you stop the flooding, then the system becomes very, very slowly usable again. And it takes a long time until, so people will just turn on, turn off, turn on, and oops, still flooding, fuck. Yeah, so. Yeah, now we're coming to the fun part. If you think that's the fun part, no, now comes the fun part. Cisco, very cool, immediately made a fix available. I mean, I told them, I think, beginning of August or something. And just 2 months later, they had the first fixes out. I mean, all iOS and all other firewalls are affected. So really wide product range. But still, 2 months, and they said, here is a fix, and made it all available. Very fast, pretty cool. Yeah, Microsoft said, yeah, this is a design issue of IPv6, so we don't do anything. Okay, let me think. Cisco can fix that. Microsoft say, sorry, we can't. So who's dumb? Cisco or Microsoft here?
We're the dumps. We're paying too much for Microsoft products.
Yeah, maybe that. So Apple is not vulnerable to that problem, so they actually did something right, which surprised me even more. I don't like Apple, if nobody noticed so far. The only thing you have to do with my toolkit is run this command, and then every Windows systems on the local network is done. And the good thing is, by default, you can't protect against this attack. The only thing you can is disable IPv6 support, and you have to do this by hand. That's the only protection there is. There is no other protection. Even if you have a personal firewall on that system, it doesn't help you, because it allows these packets through. So even your firewall doesn't help you. There is no other way to protect against it, and Microsoft doesn't want to fix that. And just this morning, there's a new press article because of that, saying Microsoft should urge to patch dangerous IPv6 denial of service hole, blah, 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 blah. So this is just from this morning. So it gets more and more coverage to that they finally fixed that bug. The background to this is that the team responsible now for the TCP/IP stack, they don't want to fix such local denial of service vulnerability. Not only this one, but all others they don't want to fix, because they fear they will have to fix many, many more vulnerabilities like these. That's why they don't want that. And the IPv6, the team which implemented IPv6 in Windows originally, they contacted me and said, oh yeah, we know, and we really tried to tell them to fix it, please, but they won't. So even the guys implementing IPv6 in Windows, they said, oh, this should be fixed. But it's just the team which says, for political reasons, no, we don't. Even the security team in Windows wants it fixed, and it's not happening. So hopefully now something will change. Yeah. Yeah, it's unbelievable.
So there is no way to
disable IPv6, only option.
So Windows phones.
Also affected.
Is the program is freely downloadable?
Yeah.
But like scanning.
Yes?
Wait, but finding an actual computer with IPv6 is a bit not possible.
Yours has?
Every Windows 7.
Every Windows 7, every Windows 2008 server, all Vista systems, all Linux systems, all have IPv6.
Finding the IPv6 address.
You don't need, they must just be local on your network. That's all that is needed. Nothing else. You don't need to know their MAC address. You need to know nothing. You just need to be on their local LAN. That's all that there is.
It's like a broadcast.
Yeah. It's a broadcast on the local network. Yeah? Everybody's done. So you can try it here on the university network if you want to. But I wouldn't recommend that, of course. Okay, but I'm coming back to this stuff later because they're fixing a very minor issue. They fixed that, but not the big issue. Yeah. But oops. So okay. Another topic, because I have lots of topics and I think I'm already getting over time. We have /64 subnets, and every subnet on IPv6, wherever it is on the world, is /64. If a subnet is 4 billion times larger than the whole internet, how would you be able to do a ping scan or a live scan on a subnet? It's not possible. Yeah? You would not be alive to see the results of your scan of just one subnet. Yeah? It doesn't work. Too many addresses. So all people and all the jerks were saying IPv6, scanning IPv6 networks, that's unfeasible to do because of the large address space. Actually, I was one of those jerks. And last year, I was thinking, is this really true? Maybe there are ways around it, and maybe it is possible. So I tried to use my brain and thought about what we can do. We cannot scan the whole range. Yeah? I made really calculations. It's really not possible. Yeah? It doesn't matter how to use your calculator. It's still not possible. Okay, we don't have broadcasts which we can access from remote. So this is not working either. Well, we can use search engine databases and stuff, but we will only find that stuff which is kind of public. Yeah? So this won't help us that much. But maybe we get that DNS information from that we can use here. So let's say Deutsche Bank. Yeah? db.com, deutsche-bank.com, deutsche-bank.de. There we might find IPv6 information in that DNS server. So we look up www.see if it has an IPv6 address and stuff, so DNS brute forcing for IPv6. We can use that information. Yeah, but we find only that stuff where we can guess the DNS name of and nothing else. And if it's something is not DNS, in the DNS, And then I thought about, what about common addresses? A common address is, for example, ::1. Yeah? Or in IPv4 speaks the .1 IP address. This is the most common IP address used on IPv4. So maybe it's also the most common IP address used on IPv6. Maybe. That was speculation. So the approach I wanted to take is combining all these three methods and checking if this would lead me anywhere. Of course, this has large, big spots, black holes, in my statistical assessment. First, it's not really mathematical statistics because I don't like that stuff. I'm not, let's say, academic. I'm more practical, hands-on. The other thing is, in the DNS, you usually only find the servers. Yeah? And also, the common addresses, which I will show you later, usually are more for servers. So what we are finding here when scanning are mostly servers on DM sets or in the network, and not necessarily all the DSL clients, for example. Yeah? So this is then also the focus of this assessment. So I looked at the search engines, yes?
Maybe, I'm not sure, but if on DHCP usually the server gives the addresses starting in 1, 2, 3, the local address. How the auto-config does it?
Okay, maybe I should tell you that. In auto-configuration, the client decides what address he wants to use, and then checks by duplicate address detection if this address is already used. And either, but I'm coming to that in the following slides following 2 slides later, coming back to that. So I dumped all the IPv6 web directories I could find, and from that I found 17,000 possible domains and subdomains of companies, networks that might have IPv6 stuff in there. Might. So I did some DNS brute forcing on these 17,000 domains. I generated word lists myself. I used some publicly available on the internet. I did some IPv6 special stuff like IPv6 gateway dot blah blah blah, yeah, stuff like that, and came up finally with 3,217 host names. Tried them on these 17,000 domains and came up with, yeah, that 23,000 something DNS entries were found. I also checked the host names I were using and thought, oh, only 2,000 of the 3,200 I checked for were actually used. Okay, so already things to improve. So I analyzed the results of the DNS entries. I found 15,000 unique IPv6 addresses. So which means if we have 23,000 but only 15,000 addresses after, which means you have multiple DNS entries for one server. These were located on 7,300 networks, so I found 2 IPv6 addresses per network so far. So there should be way more, right? And 5,800 unique host addresses. And now that's the interesting part. I do brute force on the DNS, I get back IPv6 addresses, and I check what's the host part of all the results I got. And on these I did some analysis. First, this is a distribution chart, and we see that there are addresses which are used very, very often. So this is a number of total number of IPv6 addresses. This is yeah, how many there are. So like this here is 12,000 different actually it's the other way around. So let's say there are addresses which are very often used and others which are used only once. Okay. So I said, okay, up to this is interesting. If I can do just the checks for these few numbers of host addresses, I will have more luck than using any of the other addresses. Okay, so let's look further than that. And I analyzed these addresses. What are these host addresses actually? So some come from auto configuration, some were configured by hand, and some came by DHCP. Okay. So what does it mean? In auto configuration, it can happen, and now that we come back to your question, in 3 different ways. Most are using the MAC address. Yeah? So it's using the MAC address, it's flipping a bit, one special bit. It also adds 2 more hex values, and that's your IPv6 host part. Yeah? And it's that on all the networks it will ever be. That will be the IPv6 host part it will use everywhere. It can also have the privacy option activated, because this can be traced, and wherever you are on every network, you know it's this kind of laptop and it's traveled over these and these locations, because it's always the same host part. So, but with the privacy option, it changes IPv6 address every day or every hour, depends on your configuration. Yeah, and then keeps multiple addresses, because a TCP connection might be open for 2 days, for example, and to be able to keep that address, and they also keep the address alive, but only using the current one for new connection. Yeah? So this is how this privacy option works. And with a fixed random, just by some hashing algorithm on your MAC address, it generates the host part and uses this. Okay, if it's done by hand, it's either done by a pattern or really random looking. If they use DHCP, it's always sequential. I looked at various DHCP 6 implementations, and they all, if you say start with this value up to that value, you always do it sequential. So very easy. If you find one, you know what the range is. Yeah? So this is very, very easy. And with auto configuration, based on the MAC address, for example, if you know the company uses Dell, you just have a 24-bit address space you have to look for. This is class A network scanning. That's pretty easy. Doesn't take too long. If they use privacy option or fixed random, you're in bad luck, because it's random. It's too random to really scan for that. If they use the MAC address, or you know they're using Dell or Compaq or whatsoever, then it's easy for you. If it's by hand and it has a pattern, well, it's easy, because if you see what the pattern is, you know what the other addresses are. If it's random, well, bad luck. With DHCP, easy. So if we combine these 3 things, how many of the addresses there are do we get? Do we get 10% of all the addresses, or do we get 95% of all the addresses there if you combine these 3? Now the answer is, it depends. If a network administrator does it all random by hand, yeah, we get to 0%. If someone does it all DHCP only, yeah, 100%. But on average, what will be the average if we apply this algorithm on any random network? What will be the result? So this is how it looks by hand. So : : 1, : 2, : 3. That's the standard stuff. What you will also often find is that they use the service port. Yeah, for example, 80 if it's an HTTP server, 25 it's a mail server, and so on. If they have more than one mail server, it could be : 1, : 25, : 2, : 25. Or this way, they first put the service port and then count them through. Some even use the direct IPv4 address in there. And you see fun stuff like Boop Babe, Dead Cafe, and all the other stuff. You know, okay, that's a geek configuring that stuff. Yeah? But that's the more rare stuff. This here is what you find very, very often. Yeah. To how often we come in the next slide. DHCP, people always use that what they find in the example literature. That's why you always find Cisco routers with login Cisco, password Cisco, obviously. Yeah? Because it's in every exercise on Cisco, how to learn Cisco configuration, the example is, this is how you configure enable password Cisco. Yeah? Guess what I do? So same with DHCP. So this is what you find in the literature on examples how to configure your DHCP 6 server. So we don't need to scan the whole range. As they give out the addresses sequentially, we only have to scan the first 10 addresses of each address space. If we find one, then we know, okay, this might be a used DHCP address space, and scan for the rest. So, but now for the numbers. This is after I did the large scan. So scan all the networks with all the techniques, and the numbers I got from these. So this is the auto configuration part. So where we just, if we know the vendor ID that is used on the MAC addresses, we can enumerate the rest of the address space, and we see, okay, this is already a large part of the pie. The large one here, that's the one which is the easy DHCP and hand. So : 1 or the DHCP address space. And this is already a very, very large part. We have more of the random privacy stuff, bad luck. Yeah. We have the IPv4 address space here. And basically, this and also this combined together, this is what we want, because this is what we can easily scan. Oh, is the bomb going up now? Do you have to leave the building now? I will keep a watch on you. So, as we can see, we stand a chance, statistically. So, what did I do? I had my 3,000 networks, and I brute forced 3,000 host addresses based on this here and partially the DHCP stuff and stuff. Yeah, and finally I found 380,000 systems alive. Wow. So it kind of worked. And I found 8,000 networks and 2,779 unique host addresses. So my 3,000 brute forced address space actually was very effective. Yeah, but how can I find more networks than I'm scanning? Isn't that weird? The answer to that is that I also generate special error messages, and that routers on the way tell me, oh, this is an illegal packet, by the way. And that way I detect more networks on the way on the routing path than I'm actually scanning. So that's how I got more networks. So if you want to play around with that, the Google network is very nice. It's very open. The whole routing network you can scan like you want. So, and this was the same thing now with my 3,000 addresses I was scanning for, host address part. And as you can see, wow, this is really, really working. And only here I got to the, after 2,000, so after the 2,000 addresses, I get only it's used only once. So what we only need to do is scan for 1,000 addresses, and we already get 2/3 of all, statistically, of all the IPv6 addresses on the network, just by sending 2,000 addresses. And this helps us a lot. So I did some more stuff. I did a reverse DNS lookup on all the systems I found alive, so to find more domain name, host names which I could use for the DNS brute forcing, so to optimize my list there. And then so, okay, here between, can't see it here. So this is very effective with the first 50, 80 ones, but somewhere at 1,700 or something, this is an effective DNS brute forcing word list. And basically in the whole algorithm I then deployed, I did a DNS brute force on all the new domains. There I find maybe new networks. On these networks I would do a live scanning. There I might find, when I do a reverse lookup on the new alive found IPv6 addresses, more DNS domains, and so on until everything was depleted. I didn't get any more new results. And that was how I mapped the whole server network on IPv6. It was a lot of fun.
How long this take?
Actually, not so long. Two stories for that. I told my ISP. Hey, I have a dedicated host at a hosting provider, and told them, hey, note, I want to do statistical analysis on IPv6 network on how the distribution is per month, to see how the IPv6 internet grows, and then make a talk about that. That's what I told them. And then I scanned all the networks. And yeah, what could happen? I mean, who has ever scanned the whole IPv4 internet so far? For one port, for example. The whole IPv4 internet. Who has done that so far? Nobody?
Let's go.
No, I mean on your own from a server. I did several times. And you get a mass of people saying, hey, this system is scanning me, even if you just scan for port 80. Yeah, and pain in the ass. Guess how many people told me when I scanned IPv6?
0.
The first one I think was only 1. The second times were 2 or 3, and the fourth time I think it was again only 1. I did that 3 times. 3 times the whole IPv6 internet, because I was also further developing my tools for that. And then again I have to do testing. Is this does it give better speed or reliability than my code before? So I did lots of scans. And I found 1 email on 1 IPv6 mailing list saying, hey, I noticed these scans. Did anybody else see them? Only 1 answering yes, but I don't know really what to do about that. Yeah, so nobody's looking there. Nobody. Yeah. So fun playground. Also, they're
ISP treat you since.
Oh, wonderful. And I even invited them to do this presentation also for them. And they know now exactly what I were doing, and they're happy. They're fine with that. I did, at CanSec West, I did a real workshop on IPv6 penetration testing, how to do that professionally. 2 days, 2-day tutorial. There were also 2 guys from a CERT. And they did IPv6 scanning on their CERT network. And these people complained to my ISP. They said, hey, we are being scanned from, the reason is that's not only for the CERT, it's also for the government they are protecting. So it is highly sensitive IPv6 address space. And they told me, hey, we have this complaint. Are you scanning again? Because this time you didn't tell us. And I said, now I was doing a training, and this were these people from CERT, and they wanted to see all the network. And I said, oh yeah, no problem. Do whatever you want. You don't have to inform us in the future. Just, we know we can trust you.
So all the next IPv6 scans they'll assume it's you, right?
If you hack my server, yes. Otherwise not. Yeah, but I'm not doing anything evil. No?
Right.
I'm a good hacker.
Sure.
Gray hat. Yeah. Gray hat, and no hair. So how long it takes? Because one of the emails I received was, yeah, we received something like 50,000 packets in just 1 minute. Because it's very fast to send those packets on IPv6 network, because these are the most modern routers, high bandwidth, so you have really good speed. And there's nobody else doing traffic there, so no competition on the network for your packets.
Wait, so you can actually download faster speeds?
You can too.
Using IPv6?
Yeah. I found so much stuff. I can even make my packets 100 times faster than any other IPv6 packet. But I won't tell you that now, because I still keep that a secret on how to do that. So it's possible to make your packets, even from DSL line, 100 times faster than any other network which travels over IPv6. Always winning against any other packet. Yeah. Yeah. So in conclusion, all in the mouth. If I do DNS brute forcing, I find 90% of the system which are in the DNS configured, if it's server oriented, yeah? So not DSL host names, you know how they look like. Yeah? But for the server stuff, 90%. And that is just 1,900 possible DNS host names. With the live brute forcing, we get 66, with my improved stuff, 68, 69% of the systems by just checking for about 2,000 addresses. And you can scan that in about 2 seconds, but as I resend packets and stuff, and depends on the latency on the network, between 1 and 20 seconds it takes to scan one network from remote. And that's not that much more than doing a live scan on IPv4, right? So, and if you combine both things, so the DNS brute forcing combining with the live brute forcing on the addresses, we get on average 90 to 95% of all the service on the target network, with just scanning for 2,000 host names in DNS and 2,000 addresses on the live scanning. And this is very fast to do, and with 90 to 95%, finding these very effective.
So now, I guess some open DHCP servers will implement randomly chosen
I hope so.
address, and
Okay.
that's it. And then it's very hard to.
Okay, he was saying, so maybe based on that, the DHCP server will now implement a random algorithm. I hope they will do, because what I actually want to achieve is that IPv6 gets more secure. That's my ultimate goal. So I hope this is happening, but it's not only DHCP. It's also that administrators will configure systems by hand. Remember, oh, I have to do this randomly to get a little bit more security here. That's the lesson to learn from that. Not only the DHCP stuff. But there's way more than just that. One night I was in my hotel room and I was bored. And when I'm bored and I can't sleep, I read an RFC. This can really help to fall asleep.
No more gold pictures.
And I know, sometimes I'm really a nerd. So what I took at that one night was an RFC for the multicast listener discovery protocol. And I found a security vulnerable in the protocol, how it was defined, so it can deny multicast traffic on a network. And this is how it works. So multicast means you have a site, which could be this university, and you have somewhere a DNS server. Whenever you want to access this DNS server, you just send it to the designed multicast address, and it automatically, the router routes to that IPv6 address of that server. You don't need the address, his physical IPv6 address. You just use the standard multicast address for DNS servers. And it's up to the server to announce his name, that he wants to use the multicast DNS server address, and the router will see that packet. Okay, he wants DNS multicast server traffic, and whenever these packets exists on the network, it's passed on to that system. This is how it works. And it's a fundamental thing on IPv6. Multicast is the, the spine of IPv6. Without that, IPv6 can't exist. So if the router asks if it's starting up on a general time-based mechanism, it asks, does anyone wants to have multicast traffic? And this is, for example, the DNS server, and says, I want to have multicast DNS server traffic. And then this router tells everybody, any other router on the network here, if there's anything, send it to me and I'll pass it on. And this is how it works. So what I thought, okay, I can just spoof an MLD done message, which means I don't want to listen to this multicast traffic anymore, and spoof it to coming from A. What would happen? The server now knows, okay, A doesn't want to have this information anymore, so I don't have to route this traffic anymore. Yeah, sadly, that doesn't work. To prevent that, they put extra security protocol. And that is that whenever this happens, that the router sees, oh, nobody else on the network wants this multicast traffic anymore. I want to be sure. So he sends a special message on the network and saying, does really nobody wants to have multicast DNS server anymore? Yeah. So A sees that this question and says, no, 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 no. I still want to have this traffic. Yeah. So don't stop sending. Yeah. And I said, okay, this is not working. I was sad. So what I want to do first is to become the multicast query router, because there can be many routers on the network, but only one will be the multicast router sending this query, this general query message. The algorithm for that is who is the query router is very, very simple. If you have the smaller IPv6 address, you are the master. And this is based on the linked local address. But as you can configure your own IPv6 address, if I configure my IPv6 address host part with all zeros, I always win. So this is how I become always a query router in the network. So same setup. We spoof the general query message. Same he is sending, but with the source IPv6 address of FE80 all 0. Now we will be automatically the master query router, because he sees, oh, he has a small IPv6 address, he wins. Sometimes smaller is better. Could be Japanese saying, actually. So afterwards, I can spoof an MLD done message, so all the other routers which might be on the network get informed, nobody wants this multicast DNS server traffic anymore. And I can just omit the general query message, the special query message saying, does anybody still wants to have this traffic? I can just omit that, and no traffic would flow to this network anymore for DNS. So this is how I can play it. But there's still one problem. I have to send this general query message in a specific interval. If I don't do that, this router will start again sending this message. So he will say, oh, this router is not available anymore, so I have to be the general query router again. Which would result in that this system says, I want to have multicast DNS server message. Yeah, fuck. Yeah, so this is only a temporary solution. But I want to have a solution which works forever, always. So we must send the MLD general query message in a way that the router sees that, but A is not seeing it. So it's not sending the, yeah, I want to have this traffic. No, you have to use a special target multicast address for that. Otherwise, this router thinks you're not sending it. Yeah? But there's another way you can do that. And I came up with, hey, why not using special MAC addresses for that? And that is something many people don't realize, that you have multicast MAC addresses. Everybody knows the broadcast address, all F MAC address, and, well, the MAC address of the system. But there are also multicast MAC addresses. This helps, so the system is only checking a packet if it has a special multicast MAC address which matches the multicast IPv6 addresses is listening to. Now, so this is for performance. So if we spoof the query message with the multicast all router MAC address, only the router will receive it. So it works like that. We spoof the general query message. We spoof, yeah, nobody here wants DNS multicast traffic anymore. And then after that, we send the general query message with a special MAC address, which is only for the routers. So the host systems, the server systems, will not pick up the packet. So I can send this message on this special interval. This will always be happy, never sending itself the general query message. And that way, no DNS traffic is ever getting to that network. And that DNS server is never getting the queries. Yeah? So that was the attack I found on this protocol. And then I also wrote a tool to do that, yeah, to fake all these message stuff and things. And now my question is for you, how long did that take me? What do you think?
Half an hour?
Now actually it took me 2.5 hours. To read the RFC, come up with the attack, finding this multicast way of bypassing that, and writing the tool 2.5 hours. And I don't tell you that to say, oh, this guy is cool. Now, anybody can do that, because it's so easy. In IPv6, you don't have to look very far to find vulnerabilities, because there is no security in there. So finding issues is really, really, really easy. And as nobody's doing that, so far it's only me standing here. So if you start looking for that stuff, you can be standing here next time. Wait, I'm not done with my presentation yet. Yeah. Then I came up with a different idea. Anybody sniffing on the network? So kids, in 1998, I found a vulnerability in IPv4 where I could detect if a Linux system was sniffing on the local LAN. And I could apply the same mechanism again for IPv6, but now working for way more systems. The only thing we have to do, we send a ping to a target with an unused multicast MAC address. And if we get a ping reply, it's because the system is sniffing. If we don't get a reply, it won't pick up the ping because the multicast MAC address doesn't match the target. It's as simple as that. And Windows, Linux, FreeBSD, and maybe more systems are vulnerable to that. That's all you need to send a packet, and you see if the system is sniffing or not. And now the big surprise, this is something Microsoft is fixing.
Does it work in
It's a local LAN attack, exactly like the denial of service attack. It's not denial of service anything. It only picks up if the system is sniffing or not. So, yeah, it's not really a security issue, but they're fixing that. I don't know why. Makes no sense for me. Yes?
Does it work in IPv4 as well?
It did work in IPv4, but then was fixed. But if you ask now if it also works with the multicast MAC addresses on Linux and Windows, it could be. When I sent the announcement to full disclosure and daily Dave and stuff, I wrote in there that it could also exist this way for IPv4, but I didn't check, I didn't care. Somebody else, you can check it if you want to. It's very easy to do.
Just put the source address on layer 2?
Exactly. Just use a destination MAC address of 33333 and then all 0, for example, and see if you get a ping reply with that MAC. That's it. Yeah.
So where did they fix? In the sniffer?
No, this is in the kernel. It's not fixed yet. It's the development team which told me, yeah, this will be fixed. So it's not fixed yet. You can still do that, but it will be fixed in the future. But it's just a small issue, so I can talk about that. It's not really a risk here. Yeah. Then I also took another. So what's a side channel? Because in 1990, when it was 97, side channels were a big issue, big security topic. So if you have IPv4 and TCP, is there a way to put secrets in that protocol so it bypasses the firewall and you can extract the information afterwards? So for example, military information, by just using TCP IP and not putting anything in the content of the data, just with the TCP IP protocol fields, can I hide information in there and let it travel out through the firewalls? And they found some issues and so on. Then I was thinking, okay, let's take a look at IPv6. But it took me more than 2 minutes, because everything in IPv6 is a possible side channel, and really everything. And I even wrote a tool to prove that on all firewalls, you can channel out with one packet 1 kilobyte of information through all the firewalls. 1 kilobyte. It's not like in IPv4 where you had, okay, per packet I can maybe get 6, 8, 12 bits information out of it. Yeah, it's 8,000 bits. Because everything can be used as a side channel. And all the firewalls, they don't even inspect the extension headers. Because the IPv6 is so complex, they changed the security model. The firewalls only have a list of, this is evil, and I'll filter it out and let pass everything else. And I asked, for example, Cisco, why are you doing that? And they're saying, yeah, if there is a new feature in the extension headers, we would filter that, and then something would not work, and customers would complain. That's why we do a blacklist approach, instead of what you know in IPv4, the whitelist approaches, only allowing what we know is okay. And that's why you can use everything in IPv6 as a side channel. So this is really not big interest field.
Tunneling would be easy.
Yes, you can tunnel everything. Yeah. Is there help? So this, in my former presentations, I didn't talk about, is there anything we can actually do about these topics? And of course, there are people who are telling you, yeah, there's lots of stuff you can do. Yeah. For example, there is send. SEND means secure neighbor discovery. And this is a cryptographic solution which is added to ICMP, which should authenticate all ICMP messages, which is used for neighbor discovery, router advertisement, auto-configuration, and so on and so on. But they are not telling you that this will not work. I already have 2 attacks on SEND, which I will not publish yet, which will defeat SEND. Further, there's a null of service attack on SEND that's already in the public THCP IPv6 package. And yeah, the problem is all systems must support SEND. And it works the same like IPsec, which means every system must have a certificate. Yeah? And now try to get SEND support and a certificate, for example, on all your local printers on the network. And then you immediately notice this is not happening, this will not work. The administrative overhead alone of SEND and IPsec is way too much effort as you will ever see it, except of something like military grade networks or something, and even there. Yeah? That's why SEND is a bad solution. Then we have router advertisement guard. Router advertisement guard is an idea by Cisco of selling more switches by saying, yeah, we can use the switches to see if someone is doing router advertisement flooding or trying to fake being a router and doing man in the middle through that the switch looks if that port is allowed to send those packets. And here too, I have several attacks on that protocol, which I will show at my next conference actually it's already next week, where I also release a new update of my THC IPv6 packet, which has all the tools on how to defeat this security mechanism. So watch out for that one. Well, but yeah, don't be scared. If you're the hacker, well, because there are so many ways to get around security they try to do. So in IPv6, it's complex. It's really complex. So every time I make a stop on IPv6 and do some other stuff, like working on Hydra or some whatever weird stuff, and I come back to, okay, I have this idea on IPv6, let's implement it. And it's like, oh, how do I do that? Oh, now this is not working like that. Oh, I forgot that. Because it's really complex. It really blows your brain the more you look into that. If you just look basic IPv6 header, easy. All the extension headers. And what happens if you put this extension header before the other one? How if you duplicate several extension headers? It already gets very complicated. Now, if you then add multicast and all the upper level protocols to that, which you need for multicast and stuff, it gets very complex. It's a really intellectual challenge. Now, and all the vendors make the big mistake of applying IPv4 knowledge on IPv6, and this is not working. And that's why you see all the vulnerabilities there, and all the future one I will publish at later dates. So if you're tired of finding the 100th cross-site scripting vulnerability in some PHP guest book nobody really uses on the internet, and you want to do something more fundamental and fun, and same easiness, because finding cross-site scripting in some random PHP stuff is easy, yeah, same easiness level. Join me, explore IPv6 and start hacking that. Because there's really so much to do, I can't cover that myself alone. Yeah? This is one of my favorite pictures, cocaine, so much cocaine. I rephrased it for myself, which is IPv6, so many vulns. So IPv6 really has low-hanging fruits, really so low-hanging, it's really not even a challenge. Yeah, so every time I do such an IPv6 talk, I think people seeing me saying, yeah, but it's so simple stuff. Isn't there any complicated stuff, really challenging stuff you found? Yeah, and my answer for that would be, I could maybe, but I don't need to. Not yet. Yeah. So join me research on IPv6. We can have lots of fun together. Okay, I will make the slides downloadable. Ask him on how to do that, where he will put it up. This is how you can get IPv6 tunneling to your home DSL router, for example. Yeah, I'm already way over time. Lots of stuff I have in the THCP IPv6 packet, but there are two parts of it. There's a public one and the private one. The public one is because it's public for everyone, but there's a private part. The private part has way more powerful tools, like all the alive scanning techniques. This stuff is not public yet because it's really powerful. But everybody can get access to that if you join me exploring IPv6 security. So if you send in patches, new tools and stuff for the THCP IPv6 package, you get the full private package, even with SVN access to check it out on a daily basis or hourly basis if you want to. Yeah? So public version is updated every 6 months. Next time is in 1-2 weeks. So if you want the real cool stuff, join me in IPv6. This is the URL where you can download the toolkit, also the denial of service stuff. It's all in there. The MLD attack tools are also in there. Everything in there. Something like 20, 25 attack tools in there. So lots of stuff I haven't even talked about here. They even have some hidden vulnerabilities I haven't even discussed in any conference so far. Are hidden in there. Yeah, maybe at some times, don't know if it will be June. I'm planning to do a wiki on IPv6 security and hacking, so how to do proper IPv6 pen testing, how to configure your Windows system in a way that's secure, or your Cisco firewall, how to make it secure. Yeah, so a knowledge wiki for IPv6 security and hacking. Yeah, if you know someone who is good with clone, that guy would help me, or that girl. You had a question?
Yeah, I wanted to ask, did you try to exploit the mobility features of IPv6?
It's also in there, yes.
Seems like it's really interesting how it's working.
Okay, this is very simple to explain. You send an ICMP message and say, I want to have my traffic, this is my public IPv6 address and I want this traffic to this IPv6 address now. And it's protected by IPsec.
Oh, I see.
Yeah? So if you have the IPsec certificate, of course, everything is easy. So this attack only works if IPsec is configured as optional. Yeah? And then there's a tool with that also in the package, where you can steal all the traffic for that poor person. Yeah, if you want to contact me, that's my email address. Add anti-spam to the subject line, because otherwise my anti-spam filter will just filter that out. Yes? Okay, if it's more general question, let's put them afterwards. Some THC news. I just did a Tel Aviv THC release on Hydra, just because before I left here. Now has Oracle modules, so we can now attack Oracle too. SNMP user enumeration is, no, that's not true, not SNMP, that comes in the 6.4 release. SMTP, it's SMTP. I was too tired when I wrote that. SMTP user enumeration. Some bug fixes and so on. So this is out since Sunday before I flew. You can download it there. There's also a THC t-shirt contest. Yeah? So this, every 1-2 years we make a THC t-shirts for the members and friends. And if you come up with a cool design and your design wins, send it in. Yeah? There's a URL on how to send it in. And you win, you get a free t-shirt, you get lots of free beer the next time you meet any one of our members, and you get also the free t-shirt of the next year, or in 2 years, whenever the next t-shirt is. You get 2 t-shirts, THC shirts, and there are not many of them every year, so very few. Yeah, that's it. Have fun exploring IPv6, and now if you have any more questions, this is the time to ask. Yes? Yes?
You said that they're limited to local networks only, right?
Yes.
So what does it define as a local network?
Ah, okay, yeah. IPv6 is a big topic, so explaining whole IPv6 in just a few slides is really a challenge. So what it is that the host part is just the type of service, yeah, like the TCP port, UDP port. Like : : 1 means everybody on the local LAN. Yeah. : : 2 means all routers on the local LAN. Yeah. FB, yeah, hexadecimal FB means multicast DNS, and so on and so on. Other questions? Yes, behind there.
What's the most interesting IPv6 host you found?
You find so weird stuff. For example, you ping a machine, you get the answer from a completely different machine with a different IPv6 address and stuff like that. Yeah, so really weird stuff. Yeah, so yeah.
Now,
Hard to answer that question actually, because lots of stuff is weird in IPv6 when people deploy that. Sorry, hard to answer.
what would be your recommendation?
That would be a completely different talk, yeah.
Okay, but just in a few sentences. We need to upgrade from IPv4 to IPv6 all the software that was dragged for a few years.
Yeah.
What is your approach to this in order to achieve something that is secure?
Oh, that's a big question. Let me start with one thing. What most people don't realize, people think we have IPv4, now we get IPv6, and we will have two internets in the future with some crossovers. This is not the case. The goal is to eliminate totally IPv4 in the next 5 to 7 years or something. That's the goal. Will that happen? I don't know. Yeah? I would speculate not so much, but IPv6 will be the important internet in the next 5 years. Yeah? The one which the majority will use. Yeah? So what to do with that? The problem is that the protocol is fundamentally broken, and in my opinion, unfixable broken because of the complexity. Yeah? So my recommendation would actually be, if you want security, don't use IPv6. Yeah, but of course that's not an option now that we don't have IPv4 addresses anymore. So we have to do all we can to secure IPv6 as good as possible, and actually that's what I try to achieve with these presentations, show you these are the risks. Do something, people, do something. For some things it's easy, for example through the flooding attack. Yeah? Just allow a maximum of 16 IPv6 addresses on the network adapter. Yeah? Easy to implement. Microsoft say, oh, too complicated, and it's in the protocol design and blah, 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 blah. Yeah? But it's easy to do. Linux does that, Cisco does that, it's easy to do. Yeah?
Why not just scope out IPv4 ranges instead of going into IPv6?
Yeah, but this might give you only 6 to 12 more months, and then you have the same problems again, which is actually a human problem. Yeah? If it's not about sex, people try to avoid any change as possible unless you can't avoid it anymore. So, oh, there's something coming, a car is coming, oh, still enough time, yeah. Oh, now I have to do something, fuck. Yeah? So this is how it works, how humans work. And now that's the problem. We have to use IPv6 now, but we're not there. IPv6 is actually not ready to be used for that now.
Yes, but the thing is, like, the problem with IPv4 is there is not enough space for all the devices.
Yeah.
But then again, if you have like a company with 1,000 computers, if they all have their own space of like IPs, and then if let's say the company is really big, they can separate it into 2 separate browsers.
Yeah. Okay. Still, this is only helping you maybe 1 or 2 more years. And if you're a mobile company provider, you have big issues because, okay, 10 dot something address space, yeah, but you have more subscribers than that. How would you do that? So, for example, T-Mobile does already network address translation, more network address translation, and until you're on the internet, because different country, overlapping IP address space, too small IP address space in the total 10 dot something network for all their subscribers, problem. Yeah? So they want IPv6 because they need that. Okay, let's say 2 last questions.
From your experience in Linux, how is the development going in order to solve a few of the problems that you showed?
Well, the stuff I'm presenting, they're trying to fix, like Linux stuff, the router advertisement flooding. They fixed that even before I found that, because someone thought, oh, this might be a problem, so I better put something in there. Yeah? So if you fix the stuff, still the redirect issue, the neighbor discovery spoofing, it's all still in there. But we have that already also with IPv4. Yeah? But with IPv6, you have more options to use these attack vectors. So that's basically the problem. Wait, last question is there?
What you presented here, for some of the issues, it seems like, as you said, the protocol itself is broken, and vendors cannot do it because that's what the RFC tells them to do.
Mm-hmm.
So,
but then again, when did ever Microsoft, for example, take care of any RFC? C Kerberos, for example.
Microsoft, but if the vendors would like to do, there are some issues that the RFC prevents them from doing. Maybe with your experience with IPv4, which I presume had the same problems, how does the IETF handle those issues, and do you expect?
There was an RFC about that, I think a month ago, and it's called a problem statement. Problem statement means, now we are aware that this is a problem. Let's see what we find to solve that. They're not at that point yet. They're now officially acknowledged the problem and put it down to workshops to see what they could do. So far, it seems that they recommend IPsec, send, and router advertisement guard. And that's all not a good solution. I don't know if there actually is a good solution. Maybe there isn't.
And another dot to the IPv4.
Wonderful. Okay, final question.
Of course, traffic hijacking problems come from a higher level protocol, for example, SSL and stuff like that, and not trying to use the network to make sure you get to the right routers all the time, because that's really hard to protect the path that a large portion of people from your domain.
Mm-hmm.
So I will protect from people from stealing my traffic in the local network, and then send it to my ISP who doesn't really know what he's doing there is.
Mm-hmm.
So it seems like attempting to protect something that is not that credible.
Well, that's one thing what you try to do, for example, on the public networks, that you try to put the security on the upper network protocols like SSL and stuff, but then we all know SSL is totally broken. I mean, you're all from Israel, you all know that Mossad can create any SSL certificate for any browser they want to. So how much security do you have in SSL?
Really too much.
Okay, thank you for listening. I hope you enjoyed it. Excellent talk. Thank you.